Okay, so in the last lecture, we were talking about the noise performance of frequency modulation, and we stopped with an example, and I asked you to think about the example. Let's go over it together. We have a message signal with 10 kilohertz bandwidth and power 0.5 watts. And this message is transmitted over a channel with bandwidth 120 kilohertz, and the noise PSD is given. All right. So the question asks, what is the minimum received power in order to achieve an output SNR of 40 dB or more with FM transmission? So how do we approach this problem? Okay, so I would like to hear from you. What do you think when you see this problem? First of all, what is given to us already and what is left to us as a choice? The 10 kilohertz message bandwidth and the transmission bandwidth of FM, they're both given, right? And the transmission bandwidth is 120 kilohertz. So what does that tell us about, for example, the beta of FM?
Beta 5 oluyor hocam. Tüm bandwidth kullanırsak.
Right. So basically, that's we can immediately infer, and that's fixed. Essentially, beta has been specified in the problem as 120 over 10 minus 1. I'm sorry, 120 over, 60 over 60 over 10 minus 1, which is 5. Why? Because they're telling us, let me repeat this. They're telling us that the transmission bandwidth is 120 kilohertz. And we know that this is approximately equal to, via Carson rule, twice beta plus 1 times W. All right. So now, so with that, what else can we do? What else is known? SNRO is specified as 40 dB. Well, we know that SNRO is given by the figure of merit multiplied by the SNRB. Multiplied by SNRB. What is the figure of merit, provided we are above threshold? That is, if FM is operating in the above threshold mode, this is given by 3 beta squared P sub M, provided the carrier to noise ratio rho is much bigger than 1. Okay, significantly bigger than 1. So we would be safe if rho is 10, for example. Now, provided that this is satisfied, which we have to check, then essentially IFM is given to us, right? 5 squared times 3 times 0.5. That is 37.5. Right? So, so this is given in the problem as 37.5. Right, and this SNRO is desired to be bigger than 40 dB. What is 40 dB? 10 log times the output SNR is greater than 40. This means the output SNR is greater than 10 to the 4. Okay, so this is asked to be bigger than 10 to the 4. Okay, how about SNRB? SNRB is the received power divided by the power in the message, noise power in the message bandwidth, right? What is the noise power in the message bandwidth? And not W, right? Right. So basically, we are asked that PR over N naught W times 37.5 is bigger than 10 to the 4, which means that PR is bigger than 10 to the 4 times N naught W divided by 37.5, essentially. And not the, what is N naught W? This is 10 to the minus 20. And let me admit one more person coming in. And W is 10 to the 4. This is 10 to the 20, this is 10 to the 4. So 10 to the minus 12 over 37.5, if I'm not mistaken. Right. So that's the requirement on power. So effectively, now we have solved the problem, but we still need to check that we are above threshold. So how do we check that? What is the CNR? The CNR rho is given by basically the CNR rho is PR, right? Or AC squared over 2, depending on which one. But right now we're working with PR. PR divided by the noise power in the total transmission bandwidth and not BT. Okay, so this is 10 to the minus 12 over 37.5 divided by 10 to the minus 20 times 120 times 10 to the 3. And the result, well, this is 3 orders or 6 orders of magnitude. This is 10. So the result is clearly above 10. So this is sufficiently large. Okay, any questions here?
Hocam, can I ask a question? While calculating the noise power, we used N0W. Isn't this W 120 kilohertz rather than 10 kilohertz, the effective bandwidth?
So here is the deal. This is the message bandwidth. W is here. Okay, and if I'm drawing here the noise PSD, it's at N naught over 2. The white Gaussian noise has PSD.
We use
Over 2 times.
do we use? Yes,
Yes.
I get this, but is this W the bandwidth of the signal or the effective bandwidth?
No, this is the message bandwidth. Message bandwidth,
Okay.
because that's how SNRB is defined.
Okay, thank you.
Any other questions? Okay. So last time we said there is a problem in FM where the noise at high frequencies is amplified. So when you think about the additive noise component at the output of the FM detector, demodulator, that is, The additive noise has a PSD that looks like a quadratic. So if you look at the noise within the message bandwidth, for example, and that's what we're interested in at the end, okay, at the end of the demodulation, because we have a low pass filter, we would be integrating this quadratic, which is not ideal because we have no noise at the lower frequencies and too much noise at the higher frequencies. And this would cause a performance degradation. Could we take care of this? Okay, could we do something to remedy the better SNR at low frequencies and worse SNR at high frequencies situation? So here's the idea. Maybe we could offset this quadratic form at the receiver. Definitely, if you could get a certain low pass filter characteristic that counters this effect, so that it's high at zero frequency and tapers down at the edges. But of course, that would distort the received signal. Okay, so that's a starting idea, but that would distort the starting the message itself. So the solution is maybe we could pre-filter the message such that when we apply another low pass filter at the demodulator, the signal will not be affected, whereas noise is affected in the desired way. So place a filter at the transmit end to meet, which we're going to call a pre-emphasis filter. The pre-emphasis filter is going to be a high pass filter. So we high pass filter the message with an appropriate filtering operation, FM modulated, and at the demodulator, the demodulation process is followed by a de-emphasis filter, which takes care, of the effect of the high pass filter here, such that ideally when you multiply HP and HD, you get unity, you get identity. So the message is not affected at all, but the noise is affected. Okay, so we could actually do this with a very, very simple circuitry based on just an RC circuit. So think about this simple filter characteristic, which has this frequency representation. So the corresponding inverse filter, this is clearly, it is invertible, right? The inverse filter is obtained by inverting the transfer function. So HD of F is this. Let's see what would happen if we used HP as the pre-emphasis filter and HD as the de-emphasis filter. Let me emphasize here that these are not the only choices for pre-emphasis and de-emphasis, but these are easy choices. And let's see what the resulting SNR is going to be. So let's study this system. Since the signal, the message M of T, goes through both HP and HD, and HP times HD is identity, the signal is not going to be affected at all. The power spectral density of the noise is going to be changed. So let's compute that. The noise, this is the incoming noise, but at the end of the FM demodulator, as you know, we have this additive noise component, which was the result of our approximate analysis, valid under the high SNR regime, above threshold FM operation. So you know that's the one that has the PSD that is quadratic. Suppose we pass it through the de-emphasis filter. the de-emphasis filter characteristic magnitude squared gives us this. When you multiply, you find something that looks like this and integrate it over the message bandwidth. Okay, the total power can be shown to be given by this expression, 2 and not f0 cubed, where f0 is of course coming from the circuit parameters. It's a part of this filter structure, over AC squared, W over f0 minus arctangent W over f0. Okay. We'll only be able to understand what's going on when we plug in some numbers, obviously. Let's check the improvement. The SNR out with the pre-emphasis, de-emphasis versus SNR out without using pre-emphasis or de-emphasis is equal to the ratio of the output powers in both cases. Okay, I mean the inverse of the ratio, clearly, because signal to noise ratio, and noise is in the denominator. So we're looking at an out without pre-emphasis de-emphasis filtering and an out with pre-emphasis de-emphasis filtering. Without, we have this expression which we computed last time, and with, we have this expression. So if you look at the ratio, this is the ratio. Okay, so let's plug in some numbers. With commercial FM values, for example, 15 kilohertz message bandwidth, PM 0.5 watts, let's suppose FO is 2.1 kilohertz and beta equals 5. Let's find the improvement factor. Well, so when we compute this, with the given values, it turns out the ratio of SNR-O with pre-emphasis, de-emphasis to the regular one is 21.3, which corresponds to a 13.3 dB improvement above plain FM. Plain FM already had a 15.7 dB improvement with these values compared to a baseband system. Okay, because we computed the figure of merit to be 37.5. So overall, there's a 29 dB improvement above baseband. Okay, so if you're going to use FM, it is important that you use it together with pre-emphasis, de-emphasis. Otherwise, you're leaving your system disadvantaged for no reason. So with that, let's take a look at a general comparison of the noise performance of, in general, the trade-offs between different analog communication techniques that we have studied. Well, in terms of bandwidth efficiency, who is the most efficient? Clearly, SSB with no carrier is the most bandwidth efficient technique because the transmission bandwidth is equal to the minimum possible transmission bandwidth that we can use to transmit the given message signal. It is equal to the signal bandwidth. Of course, it is not suitable for signals that contain a DC. For those types of signals, we make a compromise and use vestigial sideband. And this has been used very, very successfully for many decades with analog TV broadcasts. Okay. Now, in terms of power efficiency, we've seen that FM has many dB more efficiency over amplitude modulation systems. It has high noise immunity, and that is the reason behind its power efficiency, provided, of course, you can use FM above threshold. Now, because of this high noise immunity, FM is usually used for transmission of SSB modulated and FDM multiplexed voice on line of sight and satellite links. So first use SSB to modulate voice and FDM multiplex many channels, and then transmit them by FM to get extra noise immunity. Okay. Now, in terms of ease of implementation, though, FM is probably not the easiest, although it is close. It comes close. Conventional AM is easy because of its easy demodulation. Vestigial sideband with carrier also can be demodulated similarly with an analog detector. So those are clearly easy, but FM receivers aren't that hard either. Double sideband suppressed carrier and SSB with suppressed carrier require coherent detection. So they may be a little bit more complicated. So, well, double sideband suppressed carrier is also inefficient in terms of bandwidth, so it is hardly used. So that essentially brings us to the end of our discussion of the noise analysis of analog communication systems. Are there any questions?